Pluto, a distant and bewildering, more modest planet, was once a singular individual from our nearby planet group's planetary family. Anyway, later disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking divulgence. They recommend that this chilly world is on a potential compressed lesson with Neptune. Yet how is it that this could work out? Furthermore, what may be the results of such a tremendous event? Are we seeing an interesting grandiose peculiarity? Or is there another thing to this approaching endless accident? Go along with us as we investigate the expected results of a Pluto-Neptune impact. Pluto, a past planet that was minimized to a midget planet halfway because of its erratic orbit, remains a subject of interest and study in the enormous community. As per late expectations by leading scientists, Pluto's direction is hazardously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a potentially perilous accident between these two planets that could be an enormous threat to Earth. But how is such an event even possible? Pluto's venture around the Sun is unlike any other planet in our close-by planetary framework. It requires a shocking 248 years to finish a solitary circle. This implies that since its discovery in 1930, it hasn't even finished one full revolution. Anyway, the interest doesn't stop there. Pluto's way is marked by its exceptionally curved shape, wandering completely from the almost round circles of the major planets. What makes Pluto's orbit much more surprising is its tendency, determined at 17 degrees to the ecliptic plane. The way Pluto follows is much more extreme compared to the other planets. This tendency and erraticism add layers of intricacy to its orbital pattern. Quite possibly of the most intriguing parts of Pluto's orbit is its assembly with Neptune's. For about 20 years in each orbit, Pluto in reality moves closer to the Sun than Neptune, opposing what we could anticipate from their positions in the planetary system. This prompts the regular inquiry: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational impacts of different planets. The investigation of Pluto's orbit began not long after its discovery. Initially, space experts struggled to get a handle on its unique path. In contrast to other planets, whose orbits lie fairly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery developed with the realization that Pluto's orbit truly does indeed cross Neptune's. The stability of Pluto's orbit amid these intricacies is evidence of the complexities of celestial mechanics. The three-body problem in space is about sorting out how three objects in space, like Pluto, Neptune, and the Sun, move and impact each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all collaborate in a complicated manner. Terms like asymptotic libration and extension libration, along with the VSK oscillation, are part of this riddle. According to astrophysicists, what's keeping all planets in their orbits is a kind of libration. With respect to Pluto and Neptune, this term implies that whenever Pluto crosses Neptune's orbit, its position is always no less than 90 degrees away from Neptune. This spatial separation is significant in keeping their orbits from impacting. Scope libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential impacts. Another critical factor in this situation is the VSK oscillation. This is named after three researchers, VAV, Apple, and LV, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling impacts how they move, and for Pluto's situation, VSK helps us understand why its orbit near the Sun is so peculiar. Despite the apparent confusion, this oscillation helps maintain Pluto's orbit stable for a remarkably long time. The VSK oscillation shows that although things in space might seem wild and irregular, certain patterns and rules keep everything in place. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or stray off course. This three-body issue helps in understanding how these orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our planetary system, and distant stars and planets. Numerical simulations in the late 1980s uncovered that despite these steady properties, Pluto's orbit is actually chaotic, with minor deviations in starting conditions leading to massive differences over a long period of time. Anyway, these surprising properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, really monitoring the chaos. Later computer tests have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, impact Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one aiding. Jupiter's gravity also plays a huge part in safeguarding Pluto's orbit. Moreover, Saturn helps as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a steady path for an incredibly long stretch, potentially even billions of years. Maybe Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue moving safely in space without running into trouble. These characteristics are important in the larger context of the universe, for keeping the control and consistency of celestial bodies' movement. Without these factors, the nearby planetary system, as we know it, would be a place of far greater unrest and eccentricity. Bodies like Pluto might actually crash into others or be shot out from their stable orbits, leading to a cascading effect on other celestial bodies. For Pluto, especially with discussions about it potentially slamming into Neptune in the future, understanding its orbit is fundamental. This gives us a clearer picture of the nearby planetary system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of steady observation and investigation of these phenomena to better grasp our position in the universe. Exploring the depths of space frequently drives us to confront the erratic nature of celestial bodies, and Pluto's orbit is an ideal example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for analysis to figure out how Pluto moves in space. These simulations use complicated math to mimic how Pluto, along with other space objects like Neptune, pull on each other. By changing small details in the simulations, astronomers can observe how even tiny changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be wild and erratic. If you start with even a small difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. Anyway, despite this chaos, Pluto's orbit remains stable for long periods, billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it seems out of control at first. Predicting huge events, especially when they involve turbulent orbits like Pluto's, presents enormous challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While numerical simulations provide a solid tool for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to radically different results, making exact predictions an overwhelming task. Moreover, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have made enormous strides in understanding space, the case of Pluto helps remind us that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects, influencing the stability and direction of other bodies within the system. So, why are prominent astrophysicists just now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event from happening. Neil deGrasse Tyson, a renowned astrophysicist, offers a novel perspective on the mysteries of our nearby planetary system, especially the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers clever commentary on the evolving nature of celestial mechanics and the public's fascination with the neglected reaches of space. Tyson's position on Pluto's renaming is grounded in the ever-growing knowledge of our planetary system. He views the renaming not as a demotion, but rather as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and transformation. He sees the complexities of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the eccentricities of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant shifts in the future. This possibility serves as a reminder of how much we still have to discover about the forces shaping our nearby planetary system. In conclusion, Pluto's orbit is an intriguing case study of the complex interplay of gravitational forces in the solar system. While its path is stable now, the intricate dynamics between Pluto, Neptune, and the other planets mean that even the most seemingly steady orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to investigate the mysteries of the universe, they help us better understand the delicate balance that governs the movements of celestial bodies. The potential for a Pluto-Neptune crash isn't necessarily inevitable. However, it's a sign of the constantly evolving and unpredictable nature of the universe. Notwithstanding the scientific theories surrounding Pluto's orbit, it's important to consider the broader implications of these dynamics for our understanding of the solar system and the universe at large. While Pluto's journey is one of intrigue, it's also a reminder that the universe is full of secret complexities waiting to be explored. The concept of orbital resonance, especially between Pluto and Neptune, is a crucial piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a remarkable feature of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that, despite the orbits crossing, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impact.